All right. All right, now let me turn this off. Now we're going to talk about term C over here, which is involving u dot, in the integral, u dot ddt of dl. So let's take a look at the closed path integral of u dotted with d dt of dl. And when we think, there's a lot of math that we can go through to substantiate what exactly d dt of dl is. And let's just think about d dt of dl just conceptually and kind of skip a bunch of steps in order to actually prove this exactly. When we have the rate of change of our position vectors, our displacement vectors around our closed curve here, closed curve C, with time, or d dt of dl, we're effectively looking at a rate of change of displacement with respect to time. Well, we know that that's just velocity, since our curve C here is moving with the flow over here. So we're dealing with d dt of dl, the rate of change of our position effectively with respect to time. Because our closed curve C is moving with the flow, we can write this as the closed path integral of u dotted with du over here. In other words, we have d dt of dl. This over here, dl over dt, can be expressed as du. So we have the closed path integral of du over here, or rather, closed path integral of u dotted with du, as you can see here. And what we're going to do is we're going to split this in half and effectively write this as closed path integral of 1/2 u dotted with du plus 1/2 u dotted with du. We're just doing that because we're going to effectively approach the product rule in reverse in just a moment when dealing with dot products over here. Effectively what we've done is write x is equal to 1/2 x plus 1/2 x. We'll pull out the 1/2 over here, so we get 1/2 times the closed path integral of u dot du plus u dot du, as you can see over here, which is equal to 1/2 of closed path integral. Well, if we think of u dot du plus du dot u, that's just the product rule in reverse for d of u dot u. Effectively, take the derivative of this dot this plus that dotted with the derivative of this. So we're just going through the product rule in reverse over here. Well, here we go, closed path integral of d of quantity. That is just going to be the closed path integral of a perfect differential over here, which is going to give us 0. So what this means is that the fact that the closed path over here, the material curve, is being blown in the wind, all the air parcels in unison are all being blown by or vected by the background flow. They're all moving at the same velocity over here. There's no differential motion over here. Everything is moving along with you. So this particular term will not be providing any circulation at all. We're not going to be having any gain or loss of circulation by the fact that that material curve is being advected by the flow. Now we're going to talk about term A, involving a pressure gradient force, involving both pressure as well as density. And so term A, we're going to have the closed path integral, pulling out the minus sign over here, of 1 over rho del p dotted with dl. And remember also we can express del p dot dl as we talked about earlier. This is going to be equal to minus closed path integral of 1 over rho dp. Remember, del p dot dl, dp. We talked about earlier del pi dot dl, d pi. In this case, del p dot dl will give us dp. And so we can express this as minus closed path integral of dp over rho, as you can see here. And now we're going to talk about what exactly we are dealing with over here with this term. We're going to use Stokes Theorem to consider what's going on around our closed path integral of this term over here. Notice that over here, because there's a relationship between density and pressure over here, we don't just have closed path integral of d quantity. We have something over here that can't go inside our perfect differential because of the dependency between these two over here in a general sense. And therefore, this doesn't go straight to 0. but we can work with the quantity and the integrand over here in order to make more sense of what's going on with our density and pressure and how the relationship between the two of them can potentially tell us something about the circulation. So this term does not go to zero in a general sense, although we'll talk about a specific case where it does very shortly. We're going to use Stokes Theorem over here, and I'm going to write Stokes Theorem out over here. And this particular theorem is going to be telling us that we can express a closed path integral around our curve over here of, in general, u dot dl, which is talking about the tangential velocity. So if we have a closed path over here, and we have our individual displacement vectors tangent to the path dl, here's dl, dl, and suppose we are considering the orientation around the curve. These curves actually have an orientation to them. In this case, this would be clockwise of the dl's, and we can compute the tangential velocity, or the flow that is tangent to the curve over here. Now, we could take our closed path integral, and there's a lot of effort in terms of looking at every single point along the curve as far as, and then summing up all of our tangential velocities to get this quantity over here. That makes this particular quantity over here, for instance, very challenging to go around this entire loop. Alternatively, we can evaluate this particular quantity by using Stokes' theorem and expressing our closed path integral of u dot dl as alternatively the area integral, or the double integral over here of, rather than u, del cross u, or the curl of u, or the vorticity, for instance, dotted with n dA. So instead of going around the loop, we're looking at a normal vector to the loop, or effectively what's going on through the loop. This normal vector, we use the right-hand rule based on the orientation around the loop, determined in this case by dl. So if we choose dl to go clockwise, our n hat vector is going to be, in this case, pointing into the board over here, as you can see right over here, just like that. We're going to be using the notion of taking the area integral, or the double integral, of our vorticity flux curl of our velocity vector over here, when we're integrating, normal to our area bounded out by our closed path, in terms of expressing term A, which we're going to get to right now. So let's do that right now. We're going to, again, use Stokes' theorem over here as follows on the closed path integral of 1 over rho del p dot dl, with a minus sign out front over here. So we'll have minus, our closed path integral is going to go to a double integral now, integrating around our area over here, bounded by our closed path. So in this case over here, where we have 1 over rho del p, we're going to be now taking the curl of that, del cross, to get the following. Del cross 1 over rho del p. And then remember, we're going to be looking at the flux of this through our area bounded by our closed curve, dot n dA. And then we're going to use the, in this case, product rule, as you can see over here, for our del cross over here, effectively taking the derivative of this, cross this, and then added to that plus the del cross this term over here. So we're using the product rule, dealing with our del operator. That's effectively what this problem will turn into. So we have minus double integral of del of 1 over rho cross del p. That's from the first part of the product rule over here, plus 1 over rho, and then the derivative, or del, of the other part, del cross del p. And dot n dA. If we recall from earlier in the class, del cross del p goes to the zero vector over here. Now let's talk about what del of 1 over rho is. We have del of 1 over rho. We can write that as del of rho to the minus 1, which, remember, when we're dealing with rho to the minus 1, we take a derivative, or del effectively acting on that. We'll have a minus rho to the minus 2 times del of rho, the derivative, or del in this case, of rho, which can just be written as minus 1 over rho squared del rho. So this goes to the 0 vector. This vanishes effectively. And then this over here, we'll just bring this over here since we're dealing with term A, is going to be the double integral. And remember, minus sign over here is going to multiply out with a minus sign over here to just get a plus sign. And we get 1 over rho squared of del rho cross del p dotted with n dA. And that is our term A. So we can express our rate of change of circulation with respect to time as being, again, we have minus closed path integral of 1 over rho dp. That's one way of writing it. Or we can express that as minus closed path integral of 1 over rho del p dot dl. Another way of expressing it, or as we just found using Stokes Theorem, the area integral of 1 over rho squared del rho cross del p dot n dA. Now, let's talk about two limiting cases. One case where we're dealing with barotropic flows over here. When we're dealing with barotropic flows, what's happening is that contours of constant density are going to be parallel to contours of constant pressure. And so, as a result, in an atmosphere that's barotropic, for instance, we'll have our highest pressure down low in the atmosphere. This is going up with height above ground, lower pressure aloft, even lower pressure aloft. And our density contours are going to everywhere be parallel to our pressure contours over here, just like this. So in this case, looking at any point in the atmosphere where we have barotropic fluid, we will have our del P will be pointing downwards or perpendicular to our individual lines of constant pressure. And our density, or del of rho, is going to be, del rho is going to be pointing down as well. And as a result, del P, or rather del rho cross del P, which we're looking at over here for our barotropic flow, I should say barotropic fluid rather would be a more accurate way of talking about this over here. Our barotropic fluid is going to be associated with del rho cross del P going to 0. And exactly why? Our del rho points in the same direction as del P, so the angle between these two vectors is 0. Sine of 0, SINE, a sine of 0 is going to be 0, and therefore the cross product, which is dependent on the sine of the angle between these two vectors over here, is also going to go to 0. So for barotropic flow, or barotropic fluid, d gamma dt is going to be equal to 0 over here. And so as a result, in our barotropic fluid, we are not going to be generating any or losing any circulation. D gamma dt is going to be equal to 0 in the case where our density contours are completely parallel to our pressure contours. And in this particular case, we can also see that from this term over here. We can express density as being only a function of pressure. Another way of showing this for our barotropic fluid is as follows. When we're dealing with 1 over rho dp, we can express this over here where density is only a function of pressure. 1 over rho dp d rho times d rho, since pressure is only, or I should say rather density is only a function of pressure. And so when we write out dp, we can rewrite it as dp over d rho times d rho. These effectively cancel out over here. So we have, in this case, minus closed path integral of this, minus closed path integral over there of both sides. We can consider this over here, dp d rho with 1 over rho as being completely only a function of rho. So we're dealing with minus closed closed path integral of some d function f over here of rho times d rho, since again density is only a function of pressure in the barotropic fluid, and density related only to density, 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 so we can write this entire product here as being something that's only a function of density. Over here, df, d rho, our d rho's over here can now completely cancel out, and we get minus closed path integral of a perfect differential, which we know earlier goes to 0. So this is just another way of showing that when we are dealing with a barotropic fluid, our two vectors over here, which are parallel to each other, yielding no angle between del rho and del p, such that this goes to 0 over here. This is also related to this term, of course, needs to go to 0 for this to all truly be an equality over here. So everything is consistent, and we don't generate any circulation in the barotropic atmosphere associated with the lines of constant density being parallel to our lines of constant pressure.